L'Hopital's rule is a method for computing various kinds of limits. And it involves using derivatives in kind of a strange way. That kind of feels like it should be the quotient rule, but it's not. The first thing to realize about L'Hopital's rule, though, is that with many situations, you do not need it. And in fact, if you try to use it, you'll get the wrong answer. So you can only apply it in limited circumstances. No pun intended, limited. We're calculating limits. As x approaches either some number or perhaps infinity, meaning x is getting arbitrarily large if we let it approach infinity. Oftentimes, it's of a fraction. Let's let x approach 3 here. And let's, in this particular case, let the fraction be x squared minus 4 over x minus 2. First thing to realize is this is an example where you should not apply L'Hopital's rule. Isn't that weird? The subject is L'Hopital's rule. But for this particular example, we should not apply it. Why not? Because you can evaluate the limit much more simply. This function is continuous everywhere except x equals 2. In particular, it's continuous at x equals 3, what x is approaching. Because of that continuity, you should evaluate the limit just by plugging in x equals 3. No need to do anything fancy. Evaluate the limit by substitution like this. And get 9 minus 4 over 1 is 5. The graph of that function is continuous as long as x is not 2. In particular, at x equals 3, the graph's continuous. There's no holes in the graph. You can evaluate the limit just by substitution. So what's an example where L'Hopital's rule is needed? I'm going to use the same function, but I'm going to let x approach 2 instead of 3. Now, truth be told here, this limit can be done without L'Hopital's rule. And in fact, let's do it first without L'Hopital's rule. You might look at it and say, well, maybe the limit doesn't exist because maybe this function's got a vertical asymptote of 2. However, I hope you remember back in chapter 1 that you should first try to cancel any common factors. And the top, in fact, does factor as x plus 2 times x minus 2, which does cancel the common factor of x minus 2 in the bottom. And what's left over is a continuous function of x, and the limit can be evaluated by substitution to see that it's 4. It's a special example that I made where I was able to do that cancellation. If I pick my numerator and denominator randomly, probably even after factoring, there's going to be no common factors to cancel. I purposely picked one where it canceled. Why does that equality work? It's based on the definition of a limit. In particular, the fact that the limit is independent of what actually happens to the function at 2. It doesn't matter that this function's undefined at x equals 2. We only care about what happens to it when x is close to but not equal to 2. These two expressions, this fraction and x plus 2, are equal as long as x is not equal to 2. So if this one has the limit as x approaches 2, then this one will have the same one. And this one's a nice continuous function. It's got a limit found by substitution to be 4. What's really going on here is this original function has a graph that's actually a straight line with a slope of 1 and a y-intercept of 2, except there's really a hole in the graph at x equals 2. The graph, the picture of what's going on here looks like this. Slope of 1, y-intercept of 2, and well, this is not to scale exactly, but at x equals 2, there's really a hole in the graph. And the second coordinate of the missing point is 4. That's what we've just found symbolically. This is a problem for which L'Hopital's rule can be used to evaluate the limit as well. This is what's called a 0 over 0 indeterminate form. Indeterminate form. I always have to be careful to make sure I don't spell that wrong. Indeterminate form, not indeterminate. I said that wrong. Not indeterminate, but indeterminate form. Wait a minute. I wrote 0 over 0. That's not allowed. Can't divide by 0. Well, yeah, you're right, but I can still write it. Right, I can still write 0 over 0. It's just not defined. I didn't die when I wrote that, right? I didn't have to get struck down dead right when I wrote that. I wrote it. Both the top and the bottom go to 0 as x goes to 2. Right? The bottom goes to 0 for sure. 2 minus 2 is 0. The top goes to 0. 2 squared minus 4 is 4 minus 4 is 0. That's a situation for which L'Hopital's rule can be applied. By L'Hopital's rule, we can say that limit is equal to another limit, assuming this other limit exists. You're letting x approach the same number too, but it's a new fraction. This is not the quotient rule. I am not taking the derivative of the original function, but I am making a new fraction whose new numerator is the derivative of the old numerator, and whose new denominator is the derivative of the old denominator. It's not the quotient. Take the derivative of the top, 2x, put it in the top of this fraction, take the derivative of the bottom, 1, put it in the bottom of this fraction. Hey, and that's a nice simple limit. The answer is 2 times 2, 4. I get 4 again. Same answer. I have to get the same answer if that is the answer, if L'Hopital's rule is right. So once again, I did not use the quotient rule here, right? That's not low d high minus high d low over the square of what's below. It's a new fraction whose top numerator is the derivative of the old numerator, and whose bottom, the denominator, is the derivative of the old denominator. And this does have a nice simple limit that can be evaluated by substitution. L'Hopital's rule says, in this situation, these limits are equal. When this is an indeterminate form, if this limit exists, it'll be the same thing as this limit. Well, you might wonder, why do we need to bother? I mean, we did it this way, didn't we? So why bother with L'Hopital's rule? Because L'Hopital's rule can solve other problems for which this kind of method doesn't work. Here's probably the most famous example. What's the limit as x goes to 0 of sine of x over x? Can I cancel the x's and say the answer is sine? No. You can't cancel those x's. It's not sine times x, it's sine of x. You have to do it as it is, which then makes it feel like there's nothing you can do besides calculator experimentation. Make sure you're in radian mode. Yep, I'm in radian mode. Calculator, what's sine of 0.001 divided by 0.001? Really close to 1. What's sine of 0.00001 divided by 0.00001? 1. Actually, it's not exactly 1. The calculator just rounded. It's so close to 1, though, that it's saying 1. The answer is 1, but we seemingly can't do it symbolically. Well, now we can use L'Hopital's rule. Both the top and the bottom go to zero as x goes to zero. Sine of 0 is 0. X is obviously 0 when x equals 0. This is a 0 over 0 indeterminate form. I will just abbreviate indeterminate like this. Therefore, L'Hopital's rule does apply. You can use it. If it's not an indeterminate form, you cannot use L'Hopital's rule. And if you try, you'll probably get the wrong answer. If I try using L'Hopital's rule up here, I would have gotten this thing as x goes to 3, and I would have gotten 6, not 5. But the true answer is 5. L'Hopital's rule gives wrong answers if you use it when you're not supposed to use it. So you've got to check, is it an indeterminate form? This is the most common indeterminate form. So we can use L'Hopital's rule. Take the derivative of the top and the bottom individually and make a new fraction with those derivatives. Not the quotient rule, not low d high minus high d low over the square of what's below. The derivative of sine of x is cosine of x. The derivative of x is 1. That new limit is easy to evaluate. It's a continuous function of x. The answer is cosine of 0, which we know is 1. Therefore, the original limit exists and also equals 1. Another example. What's the limit as x goes to 0 of 1 minus cos of x divided by x squared? First of all, check, is it an indeterminate form? In this case, are the top and the bottom both going to 0 as x goes to 0? Yes. Cosine of 0 is 1. 1 minus 1 is 0. 0 squared is 0. This is a 0 over 0 indeterminate form. Therefore, I can use L'Hopital's rule to make a new fraction where the top is the derivative of the old numerator. The derivative of 1 is 0. The derivative of negative cosine of x is positive sine of x. And the bottom is the derivative of the old denominator. The derivative of x squared is 2x. But guess what? Still can't plug in 0. But guess what? It's still an indeterminate form. We can try to use L'Hopital's rule again. In fact, it's not too dissimilar from this problem, is it? Take the derivative of the top and the bottom, cos x and 2, and now that is something that can be evaluated by substitution. The final answer is 1/2. Bet you didn't expect that, huh? 1/2, is it really? Let's test with the calculator. Take 1 minus cosine of a small number and divide by the square of that small number. .5. Is it exactly 0.5? No, the calculator is rounding. But it's so close to 0.5, the calculator says, hey, I give up, it's 0.5. It's rounding. So sometimes you have to use L'Hopital's rule more than once. Twice in this case. Sometimes you can come up with problems where you have to use it 3 times or 4 times or 5 times or 6 times or 7 times or an arbitrary number of times. And sometimes you can use it forever and it doesn't help. But there is an answer still. So it's not always helpful. 0 over 0 is not the only kind of indeterminate form. You can also have infinity times 0. Infinity times 0 indeterminate form is what we've got here. We've got the product of two things, not a quotient. One of which x squared is going to infinity as x goes to infinity, and one of which e to the negative x is going to 0 as x goes to infinity. Infinity times 0, what is it? What does it equal? That's what L'Hopital's rule is meant to answer for this problem. Now, we saw one 0 over 0 question where the answer was 4, another where it was 1, another where it was 1/2. The answer depends on the function. Likewise here, are we going to get infinity, 0, 1, something else? It depends on what these functions are. When you have an infinity times 0 indeterminate form, the product of two things, one of which is getting big and one of which is getting small, it's best to try to convert it to a fraction. If you can. And in this case, one way to convert this to a fraction is x squared over e to the x, because that's what e to the negative x means, is 1 over e to the positive x. Now, x is going to infinity. That's not a 0 over 0, is it? But it's infinity over infinity. You converted the infinity times 0 indeterminate form to an infinity over infinity indeterminate form. I've not used L'Hopital's rule yet. I'm just rewriting the function. And just as 0 over 0 can be done by differentiating the numerator and denominator, so can infinity over infinity be done that way. Differentiate the numerator and denominator individually. But it's still infinity over infinity. So do it again. This is no longer infinity over infinity. You might say it's 2 over infinity. What does 2 over infinity equal? Well, it equals 0. Don't write 2 over infinity, though. I was just saying that for fun. It's 2 divided by something getting arbitrarily big. Such a fraction is going to get arbitrarily small. Have I really proved that this is 0? Not really. But I hope you believe me. I did not use L'Hopital's rule at the end here. Though if you did, it would give you the same answer. Don't use it. Just say this limit does equal 0. It's 2 divided by something getting very large. As x keeps getting larger and larger, e to the x keeps getting yet even larger and larger. So 2 divided by such a number is getting closer and closer to 0. So we use L'Hopital's rule twice in this example, here and here. The first step was not a L'Hopital's rule application. It was just rewriting the function in a way that makes it a fraction, so I could apply L'Hopital's rule. Yes, an infinity over infinity is an indeterminate form to which you can apply L'Hopital's rule. Just need to keep doing lots and lots of examples here. How about another example? Let's make it a little extra tricky. How about what's the limit as x goes to 0 from the right, technically, because I don't want to plug negative numbers into what I'm about to write, of x to the x power. I'm just going to say equals question mark for the moment. X to the x power. X is going to 0. So I've got a number really close to 0 raised to the same power that's also very close to 0. Like, what's 0.1 to the 0.1 power, for example? It's the same as the 10th root of 0.1. And when you take a number between 0 and 1 and raise it to another number between 0 and 1, you're taking a root, it gets bigger. Isn't that weird? But that's true. How about 0.01 to the 0.01 power? It gets bigger. You're taking the 100th root of 0.01. How about 0.001 to the 0.001 power? It's even bigger, getting close to 1. Maybe the answer is 1. That's what the calculator seems to be indicating. Let's try one more example. How about 4 zeros? 1. Yeah, really close to 1. Seems like the answer must be 1. This is a 0 to the 0 power indeterminate form. But if we're going to apply L'Hopital's rule, we have to apply it to fractions. No matter what you do with L'Hopital's rule, in the end, you have to apply it to fractions, take the derivatives of the top and the bottom. That's not a fraction. It's a power. So what do? Oh, a little bit of mathematical trickery. But it's trickery worth learning. Let's call x to the x another name. Let's call it y. And, well, you know, logarithms switch multiplication to addition and division into subtraction. They also switch exponentiation into multiplication. If I take the natural log of both sides of this equation, I can say ln of y is ln of x to the x, and then I can bring that power out in front. And, well, that's not a fraction, but through a little trickery, I can write that as a fraction, ln of x divided by 1 over x. How about that? Or if you prefer, ln of x divided by x to the -1 power. That's the natural logarithm of my original function. And that's a fraction, and as x goes to 0, from the right, ln of x would go to minus infinity, and 1 over x would go to plus infinity. This is like a minus infinity over a plus infinity indeterminate form as x goes to 0. Do you have to write the minus sign? Well, people usually don't bother. Let's calculate the limit as x goes to 0 from the right of not x to the x itself, but ln of x to the x. If I can figure out this limit, maybe I can figure out the other limit. That's the limit as x goes to 0 from the right of, by what I've just done here, ln of x divided by x to the -1 power. And yes, the top goes to minus infinity and the bottom goes to plus infinity, but we usually don't bother with the minus sign. Just write this is an infinity over infinity indeterminate form. So apply L'Hopital's rule. Take the derivative of the top and the bottom individually. The derivative of ln of x is 1 over x. The derivative of x to the -1 is negative x to the -2. Doesn't look much better, does it? I mean, we got rid of the logarithm. That's nice, I guess, but we got fractions within fractions here. And actually, both the top and the bottom are going to infinity as x goes to 0. So do we need to apply L'Hopital's rule again? No, it can be avoided. We can finish this without using L'Hopital's rule again, because what we can do is a little more trickery. Rewrite this function by subtracting exponents. Yeah, the negative sign can come out in front. Negative, subtract those exponents. -1 minus -2 is -1 plus 2 is 1. This the limit as x goes to 0 from the right of negative x, which is 0. Yeah, it's tricky, Most people wouldn't be able to do that without seeing somebody else do it first. But now you have seen it. Now, if you practice this kind of thing, you can do it. Wait a minute, is that the answer? I thought the answer was 1. Isn't that what the calculator said? Yeah, it's not the final answer. That's not the limit we're after. That's the limit of the natural log of what we're after. So how do I get the limit that we're after? Exponentiate. That's how. How do you write that? Let's see. You could, this is a little fancy, but you could write it this way. You could say the limit that we're after, the limit as x goes to 0 from the right of x to the x power. Rewrite x to the x power as e to the natural log of x to the x power. That's certainly true. E to the natural log of a number is the number. And then it turns out the limit sign can be brought up into the exponent. You might wonder why. Why is that allowed? The reason is because e to the x is a continuous function. That's why. I won't go into details, but that's something you can do. The limit can go into the exponent. And we just figured out that limit to be 0. Therefore, this is e to the 0, which is 1. Done. That's what was used right there. So yes, very tricky. Takes examples to see, takes practice to get. But it's standard calculus that people teach in calculus classes to be able to do this. Let's try one more example. By the way, before we do the other example, I will say, coming back to this one, the fact that this limit is 0, ultimately, of this fraction is why, we talked about this back in chapter 1, e to the x dominates x squared as x goes to infinity. Remember those things about domination? E to the x goes to infinity much faster than x squared does. So fast that this limit of this fraction is 0. Forgot to mention that. Here's our last example. This one's pretty similar to what we just did. What's the limit as x goes to infinity of 1 plus 1 over x to the x power? Think about what's happening intuitively here. As x gets large, 1 over x gets small. 1 plus that is just barely bigger than 1, raised to a very large power. You get a number just barely bigger than 1, raised to a very large power. Is that big or small? It depends. Let's try plug in x equals 10 here. 1 plus 1/10. Oops, not that. 1 plus 1/10. It's 1.1. Raise that to the 10th power. It's that. That's what you get when x is 10. What about when x is 100? 1 plus 1 over 100 to the 100th power. Let's try x equals 1,000. 1 plus 1 over 1,000 to the 1,000 power. This number is looking familiar, isn't it? 1 plus 1 over 1,000,000. No, that's 10 million. 1 plus 1 over 1,000,000 to the 1,000,000th power. 2.71828. How's that compare to E? It's almost equal to it. Can we confirm that symbolically? The answer is E. Yes. Again, call this Y. The natural log of Y is the natural log of this thing. by property of logarithms, that's this. By the way, this is an indeterminate form. This is a 1 to the infinity indeterminate form. Try to use L'Hopital's rule with this thing. Doesn't look so easy. We can certainly combine those fractions in the natural log to write it like that. And as x goes to infinity, this is an infinity times something close to natural log of 1, which is 0 form. Infinity times 0 effectively. But again, we want to write it as a fraction if we're going to use L'Hopital's rule. I think it might be good to use a property of logarithms to rewrite it like this. And then bring that x down into the bottom as a 1 over x. I think that might be the best thing to do. Let's try it that way. We're letting x go to infinity. Natural log of y, the natural log of this thing. Once again, do what I just did there to rewrite that like this. It may not look like it, but this is now a 0 over 0 indeterminate form. Both the top and the bottom are going to 0 as x goes to infinity. I haven't really proved that, but should seem reasonable. The top, these things that you're subtracting in the top are getting closer and closer together. So their difference is getting closer and closer to 0. And with 1 over x, as x goes to infinity, that goes to 0. So I can try to use L'Hopital's rule now. I'm feeling like it may not work, but let's see if it works. By work, I mean, is it helpful? Take the derivative of the top and the bottom individually. Simplify. Yeah, this is not so nice here. I'm going to simplify by multiplying the top and the bottom by x squared. It's one way to simplify. And I guess also get rid of that fraction there, multiply by x plus 1. It's not obvious to me whether this is going to work or not. Let's just see what happens. Multiply it through on the top, you get cancellation in various spots. You get an x squared minus x times x plus 1. And in the bottom, the x squareds cancel, leaving you with minus x plus 1. Oh boy, this is not working so nice. Oh, wait a minute, maybe it is. The x squareds cancel. I'm left with a negative x on the top and a negative of x plus 1 on the bottom. And that's a rational function where the degree of the top and the bottom are the same. You look at the coefficients of the highest power. You could also use L'Hopital's rule again. It's an infinity over infinity and get negative 1 over negative 1, which is positive 1. Yeah, this did work. So the places where I use L'Hopital's rule were here. And also right here, I use L'Hopital's rule. Anyway, the limit that we're after by the same kind of trick I showed you with the last problem, write that function as e to the natural log of that function. Then bring the limit sign up into that power. That's okay to do. And by what we just did, that limit equals 1. So this becomes e to the first, which is e. Yes, this is very tricky. I've done some extra tricky examples here. They are pretty standard examples. And a yes again in the simplest form, like sine of x over x, for example, the first few examples we did, L'Hopital's rule is fairly easy. But even though those simple examples, my experience is people have trouble with it. Never mind these extra tricky examples. Okay. So it's something to work on. And that'll be part of the homework due Wednesday. See you then.